I chose an excerpt from The Brief History of Time by British scientist Stephen Hawking. I chose this excerpt from Brief History of Time as a recommendation from a friend of mine. I also find this excerpt to be thought-provoking and very interesting. Einstein made the revolutionary suggestion that gravity is not a force like other forces, but a consequence of the fact that science-time is not flat as it had been previously assumed. It is curved, or warped by the distribution of mass and energy in it. Bodies like the Earth are not made to move on curved orbits by a force called gravity. Instead, they follow the nearest thing to a straight path in a curved space, which is called a geodesic. A geodesic is the shortest or longest path between two nearby points. For example, the surface of the Earth is two-dimensional space. A geodesic on Earth is called a great circle and is the shortest route between 2 points. As the geodesic is the shortest path between 2 airports, this is the route an airline or navigator will tell the pilot to fly along. In general relativity, bodies will always follow straight lines in 4-dimensional space, but nevertheless appear to move along curved paths in our 3-dimensional space. This is rather like watching an airplane fly over hilly ground. Although it follows a straight line in 3-dimensional space, its shadow follows a curved path on the two-dimensional ground. The mass of the Sun curves space-time in such a way that although the Earth follows a straight path in 4-dimensional space-time, it appears to us to move along a circular orbit in 3-dimensional space. In fact, the orbits of the planets predicted by general relativity are almost exactly the same as those predicted by the Newtonian theory of gravity. However, in the case of Mercury, which, being the nearest planet to the Sun, feels the strongest gravitational effects and has had a rather elongated orbit, general relativity predicts that the long axis of the ellipse should rotate around the Sun at the rate of about 1 degree in 10,000 years. Small though this effect is, it has been noticed before 1915 and served as one of the first confirmations of Einstein's theory. In recent years, even the smaller deviations of the orbits from other planets from the Newtonian predictions have been measured by radar and found to agree with the predictions of general relativity. Light rays must too follow geodesics in space-time. Again, the fact that space is curved means that light no longer appears to travel in straight lines in space. So general relativity predicts that light should be bent by gravitational fields. For example, the theory predicts that the light cones of points near the Sun would be slightly bent inward on account of the mass of the Sun. This means that light from a distant star that happened to pass near the Sun would be deflected through a small angle, causing the star to appear in a different position to an observer on Earth. Of course, if the light of the star always passed close to the Sun, we would not be able to tell if the light was being deflected or if the star was really where we saw it. However, as the Earth orbits around the Sun, different stars appear to pass behind the Sun and have their light deflected. They therefore change their apparent position relative to other stars. It is normally difficult to see this effect because of the light from the Sun, making it impossible to observe stars that appear near the Sun. However, it is possible to do during an eclipse of the Sun, when the Sun's light is blocked out by the Moon. Einstein's prediction of light deflection could not be tested immediately in 1915 due to the First World War. It was not until 1919 that a British expedition observing an eclipse in West Africa showed that light was indeed deflected by the Sun, as predicted by the theory. This proof of a German theory by British scientists was hailed as a great act of reconciliation between the two countries after the war. It is ironic, therefore, that later examination of the photographs taken on that expedition showed the errors were as great as the effect they were trying to measure. Their measurement had been of sheer luck, or a case of knowing the result that they wanted to get, not an uncommon occurrence in science. The theory of light deflection, however, has been confirmed by a number of later observations.